Today, we will be creating a microgrid using a small modular reactor, or SMR, in Xendee. This research was done in partnership with Idaho National Laboratory and is supported by the United States Department of Energy. What is shown here is Xendee's GIS design interface. Here we can set up new projects and use a satellite map of the actual site location to create microgrid designs. The interface also features a technology toolbar where we can add up to 25 different types of distributed energy technologies, as well as transmission assets like cables and transformers. Next, on the left side of our screen are the environmental factors. These can include utility and fuel prices, as well as project-specific options like outage ride-through capabilities and financing methods. Finally, the top bar can be used to share and navigate between projects, as well as run optimizations which can be set to achieve certain organizational goals such as cost reduction or CO2 emission reduction. For this demonstration, we have a multi-node test microgrid that has an electrical load and a heating load already defined. The microgrid itself is grid connected with time of use electricity rates and demand charges also already defined. Heating load is satisfied through an existing boiler using natural gas fuel that is purchased from the utility. The fees shown here are roughly the average of California's rates for the last year. However, we want to consider using an SMR in combination with heat storage to improve the economics of this microgrid. We will start by adding the modular reactor to the reactor node. The reactor we have selected is 100 kilowatts and is around $2 million in cost. As we can see, the SMR inherits many of the settings of a conventional generator. We have the per unit install costs, lifetime, and maintenance costs. However, the SMR also has unique settings such as the decommissioning costs incurred for shutdown, the front-end and back-end fuel costs, and the refueling period. The front-end fuel costs represents the loading costs of the new fuel, and the back-end fuel costs is the nuclear waste handling costs for used fuel which are incurred every refueling period per unit of SMR. In this demonstration, we will also use combined heat and power to generate electricity through steam, as well as utilize the excess heat to meet heating demand in the building. The maximum heat generation is defined by the reactor thermal rating factor. This factors the ratio between the thermal rating and the electricity rating. So a value of 3 here means that the thermal reactor power capacity is 300 kilowatt thermal. Baseload operation can also be explicitly enabled by defining a set point duration, which is a minimum amount of time before the power set point can be changed. For this demonstration, this is not set explicitly. However, we are going to set reactor maneuvering limits to the cycle depth and max cycle. The cycle depth represents the percentage of step load increase or decrease of the full electrical and heating capacity that is considered as one cycle. The max cycle, meanwhile, refers to the maximum amount of cycles that the system can withstand within the lifetime of the SMR. Next, we will save this module and add in our heat storage to the reactor node. With that saved, the heat storage can help ensure the cycling limits are met while the SMR is able to constantly produce high electricity and heat output. For this project, we will set the financing to 30 years to see the dispatch of the SMR across time. This will allow us to see the cost projections over the entire SMR lifetime. Finally, it's time to optimize our design. We'll start by naming the optimization and setting the optimizer to reduce cost. After running the optimization, Xendee has identified the ideal investment scenario, which includes 500 kilowatts of SMR and 2.8 megawatt hours of heat storage. This will result in a 31.4% savings in energy costs over the baseline. In our costs and savings projection graph, we can see that the savings will overtake the aggregate investment around year 8. We can also view the investments made by year by scrolling over the bar for the corresponding year. In year 1, we can see the investment for the small modular reactor as well as the heat storage. We can also see the decommissioning costs, represented after the 25-year lifetime. Next, by looking just at operational expenditure, we can see the annual OPEX increase after the 5-year refueling period. These represent the front-end and back-end fuel costs, while after the SMR lifetime, we will only have the back-end fuel costs. For simplicity in this model, it is assumed that the SMR will be reinvested in after the 25-year lifetime. Next, looking at the dispatch, we can see the priority is on the small modular reactor. So purchases from the utility are made only when the electricity load is higher than the 500 kilowatts of electricity generated by the SMR. For the heating dispatch, we can see that there is no heat being generated by the existing boiler. All the heat demand is fulfilled by the SMR with the help of the heat storage. So heat is stored during the times when the water heating load is low, before 7 a.m. and between 1 and 5 p.m., and then used when the heating demand exceeds the amount generated. This can be observed by the increase in state of charge and the heating supplied to storage on the graph. Because of this, the heat from the SMR and the reactor power has minimal changes and avoids large fluctuations throughout the day. This minimal change in reactor power is also enforced by the cycling limits that we set previously. Learn more about Xendee and our multi-node microgrid optimization capabilities at xendee.com. We'd also like to thank our partners at INL and support from the United States Department of Energy.